All right, so we were talking about amides last class, and amides are formed by reacting an acid chloride with an amine or ammonia. You can form this amide, right? And the reason that biochemically that's significant is because the formation of this amide bond, it shows up in our proteins, okay? So here you can see two amino acids that are put together through an amide bond. So you can see the amide right here that's formed. Okay, the carbonylamine portion, when they're bonded together, that forms the amide. All right, and so amino acids, when they form these amides, the reason they're called amino acids is because on one part of them they have an acid portion, and the other part they have an amine portion. And so that's the perfect type of molecule to continue a polymerization of these amino acids, because the amine part is going to react with the acid part of another molecule, and they're going to form the amide bond. Acid amine, amide bond, acid amine, amide bond. And you're going to continue to polymerize that peptide into a full-grown protein. Okay? So that's the significance of this amide bond. We call it a peptide bond when it's part of a protein. Okay? But it is in fact an amide that's being created. Now the amino acids are different only by this R group right here. So the R group, if you change it, you're going to change the amino acid. Everything else about it is the same. The backbone of the protein is NCC. NCC. And then when I put the new amine right here, NCC. Okay? That's what the backbone of this protein is going to be. The other thing that is significant about this amide is that proteins fold up. That's what they do. They fold. So if you have just a strand of protein, it's not active. It's inactive. It's called denatured, right? So you have a denatured protein if it's unfolded, but proteins by nature will fold. So they form these things like beta pleated sheets or alpha helices, and so these are the secondary folding parts of a protein. Okay, and the formation of these alpha helices or beta pleated sheets are accomplished through the amide here. Okay, so think about this protein strand and it's corkscrewing up. Okay, as it's doing that, the amine here is bound directly to a hydrogen, right? And it can interact through a hydrogen bond to the carbonyl of another amide bond right below it. Okay? Or this one's interacting with an amine right above it. And that's holding the structure of this together. So it's corkscrewing up, and you have all these hydrogen bonds that are holding it in that shape all the way up. So this amide formation is important for those secondary structures of the protein that we're going to discover. Okay? And also beta pleated sheets. You're going to see the same thing. These amides, the hydrogen bonding is holding together the sheet as it's going back and forth into a sheet. It will hold it together. Okay? All right. So protein synthesis uses tRNAs. And so think about how when we accomplish this peptide formation or the amide bond creation, the best way to do that is to use an acid chloride and an amine. So just think of this tRNA as a chlorine. So if I take the acid chloride and I react it with an amine, what happens to the chlorine? the chlorine does what? It pops off, comes off, right? So the chlorine's going to come off, and in the same way, what's going to happen to the tRNA? It's going to pop off, right? You don't have tRNAs in the structure of a protein. They get released. So essentially, what's going to happen is I'm going to have another I'm going to have another protein with an amino acid on it, on a tRNA come in here, and this amine is going to react here. The tRNA is like that chloride, and it's going to be released, and you're going to form this amide bond right here, and this gets broken. The tRNA is now amino deacylated. It goes off, and it can become amino acylated. You're going to put another amino acid on it. Okay, so it's going to get recharged, and you can use these tRNAs again and again and again. So whenever the body finds an empty tRNA, it's going to recharge it. Put a new amino acid onto that tRNA. Okay, and so then I'm going to get another amino acid tRNA right here. Same thing. It's going to create the amide bond, release this tRNA, and now I'm polymerizing a protein. Okay, this is all done on a molecule called the ribosome. That's where everything's going to be associated. The mRNA, the tRNAs, the amino acids and everything are going to get, the peptide bonds are going to form on the ribosome. That's where it's going to happen. Okay. Now, these amino acids are referred to as alpha amino acids. Okay. So, looking at this amino acid right here, which carbon, there's two carbons, which one is the alpha carbon? Is it carbon 1 or carbon 2? Carbon 2. Because alpha means what? Alpha to what? To the carbonyl, right? So the first carbon after the carbonyl is the alpha carbon. Remember when we do the common naming system of aldehydes or carboxylic acids, alpha, beta, gamma, we start with 2, 3, 4. We don't ever count 1 as alpha, right? So the alpha carbon here is the carbon that has the amine, the acid, and an R group. It has 1, 2, 3, 4 different things around it. It has an amine, an acid, a hydrogen, and the R group. The R group is what we change to change the type of amino acid that it is. So if it's just a hydrogen at that R group, it's a glycine. If you put a methyl there, it's an alanine. If you put a benzene methyl, it's a phenylalanine. Okay? So as you change that R group, you're changing the identity of the amino acid that you have. And that's what's going to establish the sequence of the amino acids in your protein, is the sequence of the R group. Okay? So we call these alpha amino acids. Why? Because the alpha carbon harbors everything. The amine, the carboxylic acid, the hydrogen, and the R group. That's your alpha carbon on your amino acids. Okay, oh, here's the alpha carbon. Okay, here's the R group. Here's the amine, the carboxylic acid, the hydrogen. Those are all on your alpha carbon. Okay? Okay. These neurotransmitters, don't worry about learning all this. Obviously, these are going to be amine-containing compounds. Serotonin, that's a good one. Histamine, going to histidine. Don't worry about all that. Acetylcholine, going to choline and acetate. All right, so let's go over a summary of our reactions right now. All right, so amines. Preparation of amines. You can prepare amines from nitro compounds or amides. Amines are basic. They can be neutralized. Okay? Amides. How do you make an amide? Acid chloride or an acid anhydride. One of those. They're going to react. You're going to react an acid chloride or an acid anhydride with an amine or ammonia to create the amide. Hydrolysis. In the presence of acid, you're going to produce two acids, a carboxylic acid and the ammonium conjugate of the amine, which is an acid. Okay? Also, if you react it with base, you're going to produce the conjugate base of a carboxylic acid, which is the carboxylate, and the amine, which is a base. Okay? So in the presence of acid, you make the two acids. In the presence of base, you make the two bases. All right, so let's look at this. So preparation of amines, I have a nitro group. I do reduction here, and I'm going to reduce it into an NH2. So those oxygens are coming off. I'm putting on the hydrogens. Same thing here with the amide. If I have an amide and I undergo reduction, it's going to replace the carbonyl double bonded oxygen with two hydrogens. Okay? And you're going to create an amine. So it's those two hydrogens. Amines are bases because when you dissolve them in water, the hydrogen of the water is going to be accepted by the amine, one of the hydrogens of water, and then you're going to be left with OH minus. Whenever I have an increase in the concentration of OH minus, my solution is basic. Now this is an equilibrium process, which means that not all of the amines are going to be caused to become ammoniums. Okay, about 5% of them. 5% is plenty to give yourself a change in a pH. Because when we're talking about pHs, we're not talking about large amounts of things. We're talking about really, 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 really tiny amounts of stuff. So for example, if you have a pH equal to 5, what does that mean? It means the hydrogen ion concentration, the H ion concentration, equals the H plus concentration of. Is that a big number? No, that's a small number. Is a pH of 5 basic or acidic? It's acidic. This is an acid. If it's lower than 7, it's an acid. So if it was pH of 6, the H plus ion concentration would be equal to I just had another 0 there. Okay? That's an even smaller number, right? But it's still acidic. If I have a pH of 9, that's how small the H plus ion concentration is. At a pH of 9. That's a really small number. Okay? So, but if the H plus ion, oh, by the way, is that basic or acidic? Basic. So that means that if the H plus is getting lower, what's getting greater? OH. So if I have a pH of 9 that's basic, that means my POH, or my OH ion concentration, is increasing. Is it going to be ginormous numbers of OH? No. It's going to be, so if I have a pH of 9, okay, then it's going to be the POH is equal to 5. And what do we know about POH of 5? The OH minus ion concentration is equal to, that's the equilibrium of a pH and a POH. Okay? So that's what we're talking about. So if I'm talking about these weak acids and I say that this is only 5% and this is 95% because of the equilibrium that's established, about 5% of it gets ionized, that's enough to make a significant change in the pH. You don't need ginormous amounts. You don't need the whole thing. Now, if it was a strong acid, it would be the whole thing. So with a strong acid, the amount that I dissolve is going to directly affect the pH. So if I dissolve 0.01 molar, then that's going to be a pH of 2 if it's a strong acid. If I dissolve 0.001 molar, that's going to be a pH of 3 if it's a strong acid. But if it's a weak acid, an equilibrium is established, and so there's a little more complicated way of figuring out what the pH is. There's a way to do it. You guys don't ever have to do that in this class, but I could go through and I could determine if I knew the percent, that it ionizes when I dissolve it, I would be able to determine what the pH is, right? Okay. So that's what we mean by these weak acids, and that it's a partial dissociation. That's what's going to happen with ammonia. You're going to get a partial dissociation, but you're going to make a significant change in the pH, making it basic. It's going to be a basic solution. Okay? So, amines can also be neutralized. You react them with a strong acid, then you will neutralize them because you're going to cause the hydrogen of the acid to be accepted by the base, amine, and you're going to create the alkyl ammonium chloride salt. Preparation of amides. So the formation of these amides is going to be accomplished by taking an acid chloride and ammonia or an amine, reacting them together, and that's how you're going to form your amide. And how many moles of amine or ammonia do I need? 2. Because one's going to act as an acid, the other one's going to act as a base. Whichever one gave away a hydrogen is going to become part of the amide. The one that accepted the hydrogen is going to become an ammonium positively charged ion, and you're going to form an ammonium chloride or an ammonium salt. Okay, chloride here because we're using HCl. If it was a different acid like HBr, it would be an alkyl ammonium bromide, right? If it was HF, it would be an alkyl ammonium fluoride. Okay? Anyways, so that's what we're going to form, those two products. So we're going to form the amide and the alkyl ammonium salt. If it's an acid anhydride, once again, how many amines do I need? 2. And as far as the molar ratio goes, right? I need a coefficient of 2 in this reaction. And I'm going to form the amide and a carboxylic acid salt. Because when I cleave it here, this is going to become a carboxylate, having a negative charge, and then the amine is going to get attached here, forming the amide on the other part of the acid anhydride, right? So here I'm going to form the carboxylate ammonium, because with the ammonium I'm going to have a positive charge. With the carboxylate I'm going to have a negative charge. That's going to create a salt. Positive-negative interaction creates salts. Okay? Ionic compounds are salts, like this. So we're going to form the ammonium carboxylate. Remember, when you name things, you'll always put the thing that's positively charged first in the name. Then the thing that's negatively charged always goes second in the name. Okay? So if I knew what this was, then I would call it an ammonium, maybe like formate or something. Ammonium formate, whatever the carboxylate is. Okay, hydrolysis of amides. So what did we react to form an amide, a carboxylic acid, and an amine. So if I do hydrolysis of it, I'm going to go back to those things, right? Except that hydrolysis can either be acid catalyzed or base catalyzed, right? Those are the two situations that we have. If it is acid catalyzed, my products are what? If it's acid catalyzed, my products are going to be acids. If it's base catalyzed, then my products are going to be bases. Good. So let's see. So here I have my amide. It's acid catalyzed, this hydrolysis. I'm going to get the carboxylic acid. And the ammonium product. And ammonium has a positive charge, and it's an acid. Okay? Ammonium is the conjugate of an amine. The conjugate, so an amine's a base, right? The conjugate of that base, meaning you add a hydrogen to it, the conjugate of that base is ammonium, which is positively charged and an acid. It's the conjugate acid of the base. So, in the presence of acid, I'm going to get an acid and an acid. Which means that if it's base catalyzed hydrolysis, my products are going to be what? Bases. Okay? What is the base of a carboxylic acid? What is the conjugate base of a carboxylic acid? The carboxylate. So if I do base hydrolysis here, instead of getting a carboxylic acid, I'm going to get my carboxylate. Okay? Now, since I'm using sodium hydroxide, the positive sodium can associate with that to make a salt. Okay? Because it's present. I could do that. And then I get the sodium carboxylate. All right, but the point is I'm going to create that base. Okay? And an amine. Amines are bases. So I get the base and the base. So if it's acid catalyzed, I get two acids. If it's base catalyzed, I get two bases. Okay? All right, any questions about any of those? Okay, so let's do a little practice. Get your whiteboards that I handed out.